Hey everyone, and welcome. Today we are diving deep into a really cool puzzle in the world of material science. How do you join things that, by their very nature, just don't want to be joined? We're talking about welding totally different metals together, and it's a challenge that unlocks some seriously amazing technology.
Just think about that for a second. How do you fuse something light and flexible like aluminum with a material that's super dense and strong like steel? This isn't just some academic question. It's a massive headache for engineers who are trying to build lighter cars, more fuel-efficient airplanes, and even the next generation of spacecraft. Getting this right is a huge, huge deal. So, okay, why is it so tough? Why can't you just melt them together and call it a day? Well, the problem isn't something you can see with the naked eye. It goes all the way down to the atomic level. Yeah, you heard that right. Atomic personalities. It's actually a great way to think about it. Aluminum, steel, copper, titanium, they all have their own unique properties, right? Different melting points, different densities, different ways their atoms like to line up. And when you try to force them into a permanent bond, they often fight back. It's a bit like mixing oil and water, except if this mixture fails, the consequences can be, well, pretty catastrophic. Okay, but here's the thing. There is a secret ingredient, a fundamental force of nature that can bridge this gap. It's a process that happens on a microscopic scale, and it's really the hero of our story today. It's called diffusion. So what exactly is diffusion? Well, imagine the boundary where two different metals are being pushed together with a lot of heat. Their atoms don't just politely stay on their own side of the fence. No way. They actually start to get curious, and they begin to migrate across that boundary, mingling and mixing with their new neighbors. This atomic mingling is what forms the weld. It's the atomic glue that locks everything together. And look, this is absolutely critical to understand. This diffusion process isn't just some random side effect, it is the weld. Without this atomic handshake, all you have are two pieces of metal just sitting next to each other. With it, you've created a single, solid structure. But, like in any good story, there's a plot twist. The very same hero that makes a weld possible can also become the villain. Diffusion, it turns out, is a powerful force that has to be controlled very, very carefully. Because if you let this process run wild, it's too many atoms cross over too quickly, they don't just form a nice, neat bond. Instead, they can react with each other and form brand new and often disastrously brittle layers right there at the joint, a hidden crack just waiting to happen. And this slide just shows it perfectly. On the left, a good bond has a nice, thin, controlled layer of that atomic glue. It's strong, it's tough, it can handle stress. But on the right, that's what happens when diffusion goes wrong. You get this thick, nasty layer of what scientists call intermetallic compounds, or IMCs. It's a fancy name, but just think of it as a layer of microscopic crackers or chalk sandwiched between two pieces of steel. The moment you put any stress on it, it just shatters. And we're not just talking theory here. These are real troublemakers that scientists have identified. When you're trying to weld aluminum to copper, for example, you get these brittle compounds like Al2Cu. Trying to join steel to titanium, you better watch out for FET. These are the microscopic bad guys that engineers are in a constant battle against. So how do they win that battle? How do you tame this atomic-level chaos? Well, this brings us to the really cool part, some incredibly clever solutions that scientists have come up with. Okay, this first method is just brilliant. Instead of relying on just heat and pressure, researchers like Lou and his team decided to shake things up. Literally. They add high-frequency vibrations, ultrasonic waves, into the mix during the welding process. This shake-up actually helps break apart those big, brittle IMC crystals before they can get too big, and it promotes a much more uniform, thinner, and stronger bond. And the results, they speak for themselves. In a typical weld between a type of aluminum and titanium, that brittle IMC layer was about 200 nanometers thick. But by adding those ultrasonic vibrations, they shrunk that weak layer all the way down to 120 nanometers. That's a massive reduction in the weak spot, which means you get a much, much stronger weld. So, what does this super sciencey quote actually mean? Well, interfacial failure is when the weld itself breaks, that chalky layer just cracks apart. But button pull-out failure, that means the weld was so strong that when they tried to break it, the weld held firm, and a chunk of the original aluminum metal got ripped out instead. The weld didn't break, the metal itself did. That is the ultimate sign of a successful weld. All right, on to method number 2, which is just as clever. What if, instead of just trying to manage a bad reaction, you could introduce a peacemaker to prevent the bad reaction from happening in the first place?
This approach is so smart. When welding copper to aluminum, which are known to cause problems, researchers like Kim and their team apply a super thin coating of nickel onto the copper first. This nickel layer acts like a diplomat, a barrier. It basically tells the copper and aluminum atoms, hey, you two don't play well together, so you're not allowed to mix. Instead of forming brittle copper-aluminum compounds, the aluminum forms a much stronger and more stable bond with the nickel. It completely sidesteps the problem.
And of course, the innovation doesn't stop there. We have to talk about 3D printing, right? The world of additive manufacturing is opening up entirely new ways to control these atomic dances, sometimes even after the weld has already been made.
Just look at that number, a 76% increase in strength. In one study, researchers took 3D printed aluminum, used a very thin copper layer during the weld, and then applied specific heat treatments afterwards. By carefully controlling how those copper atoms diffused into the aluminum after the fact, they could actually fine-tune the metal's internal structure, making it way stronger. That is a game-changing improvement.
So what does all of this add up to? Well, it points to a massive shift in how we approach this whole problem. We're moving away from an old-school way of doing things, and that's really the key takeaway here. For a long, long time, welding, especially with tricky metals, was a bit of a guessing game. You try some settings, test the weld, see if it broke, and try again. But not anymore. Now we're entering an era where scientists can use powerful tools to model and predict what's going to happen at the atomic level before they even start welding. And this is the incredible new toolkit that's making it possible. They're using complex thermodynamic models. There's one called CalPad, which is kind of like a weather forecast for atoms. Predicting what compounds will form, they're running simulations to watch how atoms will move, and yes, they're even using machine learning and AI to analyze mountains of data and optimize the whole process in real time. It's a completely new ballgame.
So why does all this matter so much? Because mastering this intricate atomic-level dance between different metals is exactly what lets us build the future. It's how we get lighter cars, more efficient jets, longer-lasting electronics, you name it. We're not just building things anymore. We are literally engineering our world from the atom up.
And that leaves us with one final, fascinating question to think about. For so long, some material combinations were just written off as impossible. But now that we're cracking the code, now that we can join the unjoinable, what comes next? What kind of impossible materials are we going to invent and build with? The possibilities are pretty mind-blowing.